Now let us discuss this question. So let me first make a diagram. So this is the center of a sphere, and this is rolling, and then it comes along with this obstacle, and the height of the obstacle is a by 2, and the radius is 2a, and the mass of a sphere is m. So a sphere of mass m and radius 2a is rolling with angular velocity omega. So this sphere is coming along this direction with pure rolling. If the angular velocity is omega, you can find the linear velocity of center of mass. This is because this is a case of pure rolling. So v is equal to r omega. So center of mass is moving with r into omega, that is 2 into omega. So VCM, you can say this is moving with omega velocity, and this is going in this direction with r omega. R is equals to 2a into omega. So this is the most center of mass velocity. Now question says radius of 2a is rolling with angular velocity omega along the horizontal ground when it strikes a step of height a by 2. So when it strikes a step of height a by 2, which is perpendicular to the line of motion of the sphere. So which is perpendicular to the line of motion. So this is the line of motion, and this line is perpendicular to the line of motion of a sphere. If the edge of a step is rough enough to prevent slipping, so this is given to us. This says this edge is very friction. It has friction, so it's rough enough to prevent the slipping. So there is no slipping at the point of contact, at the point of where this is going to collide with this step. So at this point still friction is enough to prevent slipping. So let us write friction is enough to prevent slipping. So there is no slipping. So this means after this step collision, still it remains in the pure rolling. You get it? Now, so question asks, so that the sphere can surmount the step without losing contact. Two things. This sphere can surmount this step without losing contact. No contact loss. So without losing contact. Without losing contact, it can surmount the steps if 23 omega is greater than 2 into under root 35 z by a, and this should be less than 7 times under root 6z by a. So this is the required condition so that it can jump or it can surmount the step without losing contact. So there are two conditions we have. This system remains in pure rolling before the jump and after the jump, and also it does not lose the contact at any point of time. So let us see how we will proceed for this problem. If you see what are the forces that is acting when it collides, at this point of time there will be a normal reaction that will act in this direction. Are you getting or not? And there will be this normal reaction, and there will be friction force that will act in this direction. So two forces are acting. One is the normal reaction. Of course, this normal reaction will pass through the center of mass, and this friction force is tangent to this normal reaction. Now if I want to do some conservation laws, let us say angular momentum conservation laws, from which point I should to take the angular momentum. Let us call this point as a O, this point as A. So at which point I should to consider the angular momentum. Now if you consider this point, these are the impulsive forces, friction is impulsive and normal reaction is impulsive, but this passes through point A. So this means these forces is not going to contribute any torque about this point. The torque of mg, that is limiting in nature, so I can neglect that torque. So the torque of impulsive forces is 0 with respect to point A. So I can say torque at A, torque about A is 0. So this implies angular momentum about A is conserved. So let us apply angular momentum conservation. So you see what happens. Initially this is coming with velocity omega, and once this collides with this step, its angular velocity just changes. So let us say new angular velocity is omega 1. Are you getting? But at this point of time even, this will have a velocity, that is the center of mass velocity, pure rolling case, so 2a omega 1. Are you getting or not? So let us try to do the angular momentum conservation. So before collision, your sphere is something like this. And now I want to do angular momentum about this point. So this height is a by 2. So this point is moving with angular velocity omega, and this is moving with 2a omega. So what is the initial angular momentum we have? So initial angular momentum we have, that is the angular momentum of center of mass plus angular momentum about center of mass. So about center of mass, it is moving with angular velocity omega. So let us say IC, that is angular moment of inertia about center of mass, and moving with angular velocity omega. So I into omega plus angular momentum about center of mass. Center of mass, that is moving with 2a omega. So MBR, B is 2a omega, and R is this height. Total height is 2a. So 2a minus a by 2 is the height. So this height is 2a minus a by 2. So this is 3a by 2. So 4 minus a, 3a by 2. Are you getting? So angular momentum will be this 3a by 2 into 2a omega into m. And I, in this case, this is a case of a sphere. For a sphere we have moment of inertia is 2 by 5 mr square. So let us say 2 by 5 m, r is 2a in this case, and this is omega 1 after omega, not omega 1. 2 by 5 mr square plus 2 goes, so we will have this 2 cancels out, so 3a square omega. Are you getting? Now we will have 2 by 5 into 2, so 4 into 2, 8 by 5 ma square plus 3a square omega. Now further you do this calculation, so we will have 15 plus 8, 23. Are you getting or not? I think 23 by 28. There will be omega also, m also here. So I have to write m. Here also I have to write m. And there will be a omega here, ma square and omega. So we will have 15 plus 8, 23 ma square omega. So this is the initial angular momentum. Let us try to calculate the final angular momentum. Once this sphere collides with this, that is the important point here we have, and once this collides with this step, so this is the step, and once this collides with this step, now this sphere will be rotating about this point. So this will try to rotate. So what will happen? This sphere is going to lift up. So this is here. After some time it will be here. So this sphere is basically doing pure rotation about this point. So now this sphere is rotating about this point. So let us say omega about this point is the rotation. So what is the velocity of center of mass? So this time velocity will be perpendicular to this line. Omega 1 into this length is 2a into 2a. Are you getting? So try to understand. Now this sphere, once this collides, this sphere will have a tendency to lift up. So about this point there is no rotation, there is no slipping. So this sphere will be lift up about this point. Let us say this is lifting with angular velocity omega 1. So the center of mass will have a velocity perpendicular to the radius in this case. That is the omega 1 into 2a. Are you getting? Now let us find what is the angular momentum you have about this point. I into omega. So L finally will have I into omega. And I have already calculated. So I comes out to be 8 by 5 ma square. So you see this is the I, 8 by 5 ma square. So L finally will have I, that is 8 by 5 ma square into omega 1 plus. Now MBR, so M is M, B is omega 1 into 2a, and this time R is 2a. So this is the perpendicular distance. Are you getting? Initially the velocity was parallel to the horizontal. Initially this velocity is parallel to the horizontal in this direction 2a omega. But once this collides, its velocity direction changes. Now this is doing pure rotation, or you can say this is the center of mass is moving in a circular orbit, and the circle is something like this. Are you getting? So circle is something like this. So velocity at each point will be perpendicular to this, tangent to this circular path. When it reaches here, velocity becomes parallel to this line. Are you getting or not? So this time L finally will have, so 8 by 5 plus 2, so 10 plus 8, 18. So this is omega 1 also. So MBR, so no omega 1. So MBR, so we have written, so MB is equals to omega 1 into 2a, MB, and R is 2a. So I have to multiply this by 2a. Are you getting? So let us see what this comes. This is 8 by 5 ma square omega 1 plus 2 into 2 4a square 4a square m omega 1. So 4a square m omega 1. So we will have 20 plus 8, 28 by 5 ma square omega 1. I think all of you are getting this one. Now if you do the angular momentum conservation, that is the final angular momentum is equals to initial angular momentum. So if you apply this, initial angular momentum is 23 by 28 ma square omega. So let me check 23 by 28. So 23 by 28 ma square omega is equals to 28 by 5. This time, let me check again. This is 23 by 5, not 23 by 8. So this is 5. So 23 by 5. I don't know from where I am writing. So this is 5, not 28. So 23 by 5 ma square omega is equals to 28 by 5 ma square omega 1. So ma square goes out. So we will have 23 by 5 omega is equals to 28 by 5 omega 1. So from here I get omega 1, 5 also goes out. So omega 1 is 23 by 28 omega. So this is the relationship between omega and omega 1. Now what should be the minimum value of omega 1? So this is the just angular velocity of this sphere when this collides. So this is what is happening. Once this is coming in this direction, this collides with this step, and once this collides with this step, its angular velocity changes. Initial angular velocity was omega and linear velocity was 2a into omega. Are you getting? But now the angular velocity changed just after the collision. Now with this angular velocity, this will try to raise up. So finally it has to raise up. So situation is something like this. Now initially it is something here. So this is rotating with angular velocity omega 1 and moving with linear velocity 2a omega 1, and this is the angular velocity is omega 1. Now after some time we will see basically this sphere has to let me make this one slightly difficult. Okay, I have to make something like this. So let us leave this one. Now you see what is happening. After some time this sphere will reach to this one, this surface, horizontal surface. So if reach to this horizontal surface, what should be the value of omega 1? We have to find the value of omega 1 so that it just reaches the horizontal surface. And again doing with the pure rolling. So if it reaches here, let us assume it reaches with, if just reaches, this means if initially it reaches here with 0 velocity, that will give you the minimum condition. Or if you want, you can assume this sphere is moving in this direction with angular velocity omega 2 and the linear velocity is 2a omega 2. And basically if I want just to reach on the surface, I will have no kinetic energy to a sphere. In that case omega 2 basically will be 0. Are you getting or not? So question says what should be the minimum value of omega? So I have to find minimum value of omega so that just surmounts this step. So in that case this sphere when just reaches here, it will have no kinetic energy. So I can say omega 2 is 0. That will be the enough condition I will have. Are you getting or not? So if I apply energy conservation, what is the energy conservation we have? So from here, let us take this is my 0 potential energy. So what is the height of center of mass from here to here? So this is 2a, this is a by 2. So this is 3 by 2a minus 3 by 2. So 2a minus a by 2. So that is 3a by 2. We have already calculated this side 3a by 2. So what is mgh? M is m, gh is 3a by 2. So this is the potential energy you have at this point of time. So I am writing kinetic energy plus potential energy. So this is kinetic energy plus potential energy here I am writing. So this is potential energy mg 3a by 2 mgh plus kinetic energy. We have two kind of kinetic energies, rotating as well as moving. So half I omega square, I is 8 by 5, we have already said, half I omega square, omega is omega 1, plus half mb square, so half m, and v is 2a omega 1. So this is my initial energy. Finally when it reaches, so this is let us say position number 1, this is position number 2. So this is energy at position number 1. Are you getting? So this is the energy at position number 2. If I write energy at position number 2, this has just reached to this position. So omega 2 is 0, v2 is 0. It has only potential energy. From this line now height is mgh, that is h is 2a. So this radius is 2a. So now we will have total energy simply as potential energy mgh, h is 2a. Now this is the process of pure rolling. So there is no loss of energy here due to the friction, because this point has a 0 velocity. So there is no power developed, 0 energy, 0 loss of energy. So I can say the total energy has to be conserved. So total initial energy, total final energy, potential energy is this, kinetic energy is 0. So I can equate these two terms, kinetic energy plus potential energy, energy conservation. So if we do that, what we will have something like this. So mg into 3a by 2, mg into 3a by 2, this is the first term. And the second term we will have, so 4 by 5 ma square, 4 by 5 ma square and omega 1 whole square, plus this will be 4 by 2, so 2a square omega 1 square into m. So this is the final term you have, and this is equals to initial kinetic, the final kinetic energy plus potential energy, that is 2m. So this value 2 mga. So let us try to solve for omega 1. So this is the minimum value of omega 1. So this will give you the minimum value of omega 1. Are you getting? If you have more than this omega 1 value, what will happen? This will surmount. So this is the minimum value of omega 1, because I have assumed this is a 0. If you have more omega from the calculated value, this will surmount, and here it will have some velocity also. So this relationship is going to give you the minimum value of omega 1. Are you getting? So here the omega 1 I will get. So omega 1 will be minimum in this case. Will be minimum. So let us try to solve this one. So we will have 4 by 5. So let us take ma square omega 1 square common here. So this term we will have. So 4 by 5 plus 2. And this side you will have, if you take mga common, you will have 2 minus 3 by 2. So 1 by 2 mga. So you can cancel m and m. A also you can cancel. So you will have omega 1 square a, and 5 into 10, 14 by 5 is equals to 4 minus 1 by 2. So g by 2. Are you getting? So you will have omega 1 whole square is equals to 5g by 28a. Are you getting? Now if you plug the value of omega 1 from the first equation, omega 1 is nothing but 23 by 28 omega. So are you getting or not? Omega 1 is this, 23 by 28 omega. So this is, omega 1 is 23 by 28 omega, and this is whole square. This is equals to 5g by 28 e. So now if I take root, so you will have 23 by 28 omega is equals to root over 5g by 28a. Now this means omega will be 28 by 23 under root 5g by 20 at a. So 28 goes inside, so we will have omega is equals to 28 into, so you can do this calculation. So this 28 goes inside, so you will have 5 into 28 g by a. If you take 2 common, so you will have, and there will be 23 also. So 2 by 23 under root 35g by a. You do your own calculation, you will get this result. So this is the omega minimum. So this means if omega is greater than this value, the sphere can surmount the step. So 23 under root 35 g by a. So if omega is greater than this value, it can surmount the step, because I have assumed when it surmounts, after the surmounting, the final kinetic energy, final velocity is 0. If this omega is less than this, so omega is less than this value, it cannot surmount. If it is greater than this value, the sphere can surmount, and after surmounting, it will keep moving. It will keep rolling with some velocity. Are you getting or not? This is the minimum velocity at which a sphere will surmount, and it will simply rest. It will simply stop there. After surmounting, it will stop. Now once again, the second condition of the, you see we have said omega should be omega has a range, that is omega should be greater than this value and omega should be less than this value. So we have found this one, first result, omega should be greater than this. What should be the condition so that omega should be less than some value? Now once again, after the collision, you see, so when it is colliding, what is happening? When it is colliding, this starts moving in a circle. So center of mass, so if you see the center of mass, after the collision, if you consider the center of mass is here, and normal reaction is acting in this direction, and center of mass will start moving in a circle. So this is the center of mass, and finally center of mass will come into this line. So center of mass is moving in a circular orbit. So this means center of mass has to satisfy the circular motion equations also. So at this point of time, what are the forces that is acting? So you will have mg that is acting. Let us say this angle is theta. So in this direction you will have mg cos theta. So in this direction you will have mg cos theta. Are you getting? So in this direction you will have mg cos theta. So if we apply equation, so normal reaction is here. For circular motion, n minus mg cos theta, and force towards the center. Force towards center is mg cos theta. So mg cos theta minus n, this should be equals to mb square by r, and b is simply omega. So you can also write m omega 1 square into r. R is 2a. Because after collision, just after collision velocity is, so this is moving with 2a omega 1, or its angular velocity is omega 1. So I can write mv square by a. So from here normal reaction will be mg cos theta minus m omega 1 square into 2a. Now this question says this does not loses the contact. So a sphere never loses the contact of this hinge point. This is the a step. So I can say normal reaction has to be greater than 0. If normal reaction is greater than 0, now you see the normal reaction value, you see, as soon as this starts surmounting up, this theta decreases. So this is the initial theta. After some time this is a smaller theta. So if theta decreases, cos theta increases. So this means at this point, even the lowest point, if this is greater than 0, it will be always greater than 0. So when this point, what is the cos theta? So this height is 2a. So this length is the radius 2a. This length is 2a. And now this height, so let us say if I make a perpendicular from here. So let me show here. So this is the cos theta. So if I make perpendicular from here, this length is 2a and this length is 3a by 2, and this length is simply a by 2. This is the step. Are you getting? I think you are able to understand. So cos theta, so this angle is theta. So cos theta in this case will be this height, that is 3a by 2 divided by hypotenuse 2a. So we will have cos theta is equals to 3a by 4. Are you getting? So let us plug. So let us plug the value of cos theta. So normal reaction is mg cos theta. Cos theta is 3a by 4. No a. A cancels out, so simply 3a. So 3 by 4. So cos theta is 3 by 4. Mg cos theta minus m omega square 2a. So let us say m omega 1 square into 2a. This should be greater than 0. So from here, what is the condition I am getting? So m goes out. So I will have 3z by 4. This should be greater than omega 1 square into 2a. So from here I will have omega 1 square should be less than 3z by at a. And omega 1 is nothing but, so let us say omega 1 should be less than under root 3z by at a. And omega 1 is nothing but, so you see in the previous slide we have discussed omega 1 is equals to, so let us check, omega 1 is equals to 23 by 28 omega. You see here omega 1 is equals to 23 by 28 omega. So if I plug that value, omega 1 is 23 by 28 omega, should be less than under root 3z by at a. So this omega should be less than 28 by 23 3z by at a, and this 28 goes inside. So we will have omega should be less than this goes inside, so we will have 7. So let us say, or let us take 4 common, so we will have 2, so 14 by 23 under root 3z by 2a. Are you getting or not? Or I can also write the same thing, omega should be less than. So let us take 7 by 23 and this 2 goes out, so we will have 2 multiply by up, 2 multiply by bottom, so we will have 6z by a. So what are the condition you have? So one condition is omega should be less than this value, 7 by 23 under root 6z by a, and the other condition you have, you check your copy, that is omega should be greater than, so this condition you have 2 by 3. So another condition you have, omega should be greater than 2 by 23 under root 35 g by a. So this is the condition you have. So if you multiply by 23, we will have a 2 into under root 35 z by a should be less than 23 omega, and this should be greater than, because I am multiplying by throughout by 23, 6z by a. Now you see, this problem is a quite good problem. What the important point we have in this problem is, first important point we have, that is point about which the collision happens, angular momentum is conserved. This is because normal reaction and friction both are acting from the same point, so they does not have any torque. Another important point we have, that is the conservation of energy. About this point of contact about which the collision happens, there is no slipping. So the point remains at the rest. So there is a simply transition of motion. So this motion is a point of contact at a zero velocity. So this will not loss of energy. So if there is no loss of energy, I can always conserve the angular momentum. Third important point we have, that is when it reaches at the horizontal surface, top horizontal surface, I can assume for minimum omega at top horizontal surface omega 2 is 0, and that case I will get the minimum limit of omega. To get the maximum limit of omega, I have to also say this normal reaction that is happening should be greater than 0. If normal reaction is less than 0, in that case it will lose the contact. So I don't want to lose the contact. So you can visualize, if we are throwing this sphere with a small velocity, it will not surmount. And if we are moving, if this sphere is moving with very high velocity, in that case it will lose the normal reaction contact. And that's why we have a limit. Why we have a limit? You can see in the daily life also, if you throw a ball and if surmounts the step, if it is going with very small velocity, it will not surmount because it does not have sufficient energy. And if it has very high energy, in that case what will happen? It will surmount the step, but it will jump and then surmount. Are you getting or not? So in that case it will lose the normal reaction. And if you are in the middle, there is the minimum and maximum, it will surmount and will keep rolling. So that's why we have a limit of omega. It should not be less than this value, and it should not be greater than this value. So this is the minimum limit, this is the maximum limit for omega. We'll discuss the next problem.